Technology. It's the rhythm of our everyday life. We're more dependent on satellite and communication systems than at any other time in history. Disruptions can affect our economy and even our safety. To prepare for the effects of such events and minimize impacts, we need to look outside our atmosphere, some 93 million miles away, at a star we call the Sun. It's our main energy source. It warms the Earth and grows our food. While the Sun and the space between may seem pleasant from our perspective, it's anything but peaceful. At its surface exists a chaotic state of eruptions and radiation. And unlike Vegas, what happens at the Sun doesn't stay at the Sun.
Space weather is essentially emissions from the Sun, radiation, magnetic field that erupts from the solar surface, pumped out into space, sometimes right towards Earth. When it impacts the Earth, it impacts our technology. That's what we call space weather.
These solar events and their effects at Earth can disrupt systems we take for granted. From causing blackouts to the power grid, to delaying offshore drilling operations due to inaccurate GPS data. Interference with communication systems can force air traffic to reroute and impact rescue response and coordination. Outside our atmosphere, solar radiation can harm astronauts and the systems they depend on. The good news is that these eruptions can be detected early. Forecasters at the NOAA Space Weather Prediction Center in Boulder, Colorado, have their eyes on the Sun at all times.
The Space Weather Prediction Center is part of the National Weather Service and is very much like a normal weather forecast office. We're here 24 hours a day, 7 days a week. We're looking at data, we're looking at imagery, we're looking at model outputs. As conditions develop, we put out alerts, warnings, and watches of imminent activity to our customers so they can take action.
In many ways, forecasting space weather is a lot like forecasting hurricanes. Those who rely on space weather forecasts, like electric power grid managers, are informed early on and can begin taking protective action.
When we see an eruption on the Sun, space weather forecasters will issue a watch. This is much like a hurricane watch. When a hurricane sits offshore of Miami, for example, perhaps 48 hours out, we too can see way in advance that something may be coming towards the Earth.
As the storm moves toward us, it hits a monitoring spacecraft orbiting 1 million miles away from Earth.
It's kind of our buoy sitting out there offshore, and that hurricane, about 30, 45 minutes before it makes landfall, we'll get the measurements from the buoy. That's what this spacecraft does for us. That big eruption that left the Sun hits the spacecraft. Now we've got the measurements of exactly what's going to impact us here on Earth, and we issue the warnings to give the power grid a heads up that the storm is now imminent. An interesting element to this whole process is that when the forecasters issue the alert, the power grid receives the alert, takes the necessary actions to protect the grid, and the average citizen never knows anything ever happened.
The number of customers who rely on space weather information continues to grow. As our reliance on technology increases, so will our need for constant monitoring of the Sun.
Space weather affects technologies. As conditions develop, we put out alerts, warnings, and watches to our customers so they can take action.
There's different types of impacts on communication systems, and the HF we call the high frequency, which is that band of communications 3 to 30 megahertz. But it's a very important band of radio communication because it's used widespread. It's used, for example, by the airlines.
HF radio is most commonly used for position reporting when you're going across the ocean airspace, which is devoid of radar. And ATC can't see you, so it's up to you to report your position and your altitude and your speed.
HF works great most of the time, except during a big flare. And during a big flare, that HF communication capability could be gone within a minute or two. So as soon as we see something happening in there, or we see a flare, it's one of the first things we do is alert the aviation community, hey, big flare, HF's going to be impacted.
Once we know that there's an event going on, then the aviation industry and the airlines can react to that. They can alter their routes over the poles. They can lower the altitudes that they're flying at, or maybe decide not to fly at all in the interest of their passenger safety.
So that's just one example of how HF is used, but the emergency response community will use it a lot too. It's one of their primary backups.
When you've lost connectivity between certain government agencies, it gives you that long-range coverage to talk from out of state to federal governments or from the FEMA locations to the state emergency operations centers.
So if we've got a big hurricane impact in the coastline, whatever big city, we've got the cell towers down and whatnot, we've got emergency communication folks in there. Those folks are very familiar with space weather and how it impacts their systems.
Here in recent years, it was used during Katrina when we had a lot of communications outages down there. It was also used during Hurricane Ike. There was an outage of the telephone circuits with the Texas State Emergency Office, so it was used in both of those situations.
So when we talk about backup, especially for the airlines, typically they'll have SATCOM, so that'll be satellite communication.
The satellite technology that emergency responders use could be GPSs, could be satellite phones, satellite data terminals.
Space weather events can impact SATCOMs. The impact can range from a nuisance to loss of a spacecraft. So we will give them the heads up. If we have space weather events, flares, whatnot, they need to know what's impacting their systems. Situational awareness is key. Time is of essence to these folks. Again, it's life and death.
The Space Weather Prediction Center has had a long-standing relationship with the power industry, so they've been aware that solar storms, the geomagnetic storm piece of that, can affect the operation of their systems and induce extra currents and loads on those systems that can either trip those systems offline or in the worst of cases, cause damage. That relationship goes back for several decades. In fact, a big incident in 1989 where part of Quebec was tripped offline that affected something like 6 million customers for about 9 hours. I think that really raised the awareness in the power industries.
When we get the alert, we watch the grid and start looking for issues. Are we seeing a decline in voltage? Are we seeing equipment failures? And we readjust the system to try to mitigate those problems, try to keep the lights on and keep it from going out.
Averaging about 500, 550 kilometers per second.
If we didn't have this early warning, we wouldn't see it until our sensor saw it. Getting more information quicker and faster before the storm hits, not during the storm, is a big improvement.
In the long term, I think what we need and what we're moving toward, the U.S. as a whole, is better modeling, fully understanding this phenomenon, understanding how it would impact specific systems.
Rather than actually experiencing a storm, we can simulate storms in our software and see what the impact is. We try to get ahead of it. We always plan that if there's an outage, how can we keep the lights on? What's the best process to prevent it?
In the end, 5-10 years from now, there's going to be a whole mix of operational procedures driven by what we do on prediction and warning. And then there also will probably be some level of hardware controls to ensure the reliability of the grid.
GPS has changed society. Most people don't realize how remarkable and how many different applications there are.
The GPS has become an integral part, not just of our daily lives as far as cell phones and guidance for our cars and mapping, but the whole system in agriculture is really relying heavily on high accuracy GPS.
So they're using GPS to plant those seeds with centimeter accuracy. And then they can come behind it and irrigate and fertilize right where that seed is with that 1 centimeter accuracy.
The GPS creates a line for the operator that he can steer along, or you go to another level and the operator doesn't steer anymore and the tractor has an automatic steering system on it, much like a cruise control on a car, except for when I push the button it doesn't drive a set speed. When I push a button it stays on a predefined line.
You don't even need lights. You can do it at nighttime. You program your GPS and it's driving that tractor for you. So it's huge, and it's changing the way that the farmers farm the fields.
6 or 7 days out.
There's an interest in GPS applications from space weather side because when the sun is eruptive, it causes GPS to falter, and in some cases it doesn't work at all.
Productivity may suffer to a certain degree in that there's no way that I as a human being can steer as good 8 hours a day as a GPS system is going to do. It's going to be the same all day long. Some of the other application technologies, those are going to be gone. We're not going to have the ability to do good section control on sprayers and planters and fertilizer applicators without GPS.
We see a huge growing customer base in so many different industries, so many different sectors now relying on GPS and high precision GPS. They're all big customers for us.